Today we have Professor Dinh from Queen's University in Canada speaking. Professor Dinh did his PhD at the University of Laval in Quebec, Canada. He then moved to the University of Toronto for a postdoc for several years, where he worked on electrochemical CO2 reduction, leading the catalysis group for, I believe, 2 of those years. He was also involved in the Carbon X Prize competition taking place over the last few years. And over the last 1 year, he's been working as an assistant professor at Queen's University. Today, his talk will be discussing stable gas diffusion electrodes for CO2 reduction, and I'll let him take it away from here.
Great. Thank you, Tom. Thanks for having me. I'm excited to be here virtually. I hope one day I can visit your campus. So today I'm going to talk about developing a stable electrode for carbon dioxide conversion. I'm going to go full screen. Okay. So with this topic, I will first introduce a little bit about the decarbonization challenge, a little bit about the electrochemical CO2 conversion process before we jump into the designing the electrode, where I'm going to focus on 2 main parts: develop a polymer-based gas diffusion layer, and also design the gas diffusion layer for membrane electrode assembly system. So one of the biggest problems facing humans, we know, is the climate change. And one of the reasons for that is the amount of the CO2 we emit to the atmosphere. So right now we emit about 40 gigatons of CO2 per year, and more than half of that amount of CO2 stay in the air. And that leads to the increase in the CO2 concentration in the atmosphere that causes a global warming effect. So if we continue with this trend, there's no action in terms of CO2 emission. We are on the path of increasing the global temperature by about 3.6 Celsius degree by the end of this century. And if we want to keep the global temperature increase below 1.5 degree, so that is blue curve here. So at some point we need to bring the CO2 emission go to the 0. So somehow we need to go from 40 gigaton to 0, maybe in about 50 years or so. Just to give you a sense of how much is 1 gigaton, imagine that the total weight of the human population on Earth is 0.4 gigaton. So we emit 100 times amount of that weight. So if we want to deal with the CO2, we need to know where it's come from. And by far, the energy sector is the biggest emitter, accounts for more than 70% of the CO2 emission. And if we look at where we get the energy, and it makes a lot of sense because more than 80% of the energy come from the fossil fuels, coal, oil, and gas. And when we burn those carbon-based fuels, we emit carbon dioxide. And less than 20% come from the renewable energy. But the good news for us is that we have a lot of renewable energy, especially solar and wind. So on the left-hand side, the yellow circle here is the solar, and we have the green circle here is the wind. So the total of the solar and wind can be 1,000 times larger than the amount of the energy that we need, which is the orange circle here, about 16 to 18 tetrawatt year. And when we compare this renewable energy with the finite resources, the fossil and nuclear on the right-hand side, taking together all of the finite resources, if we continue with this trend, we're gonna running out of that fossil fuel. So whether or not if we care about the carbon dioxide emission, just for the energy point of view, we still need to find a way to use the more renewable energy. But there's a problem with the renewable energy is they are not always available. Solar and wind, they are not, it keep changing in the daytime or even the seasonal. So in order to find a way to use more renewable energy, we need to find a way to store them. not just for hours, for days, but perhaps like for months and even for years. So the technology that I'm working on and together with many groups around the world is this electrochemical CO2 conversion, where we take the carbon dioxide either captured from flue gas in a power plant or from the air. Hopefully one day we have like cheap carbon dioxide. We combine with water and renewable electricity and convert them into chemicals, different molecules. We can use those molecules as fuels, liquid or gas fuels, or then we can use it as a precursor to make chemicals, polymers, for example. So with those gas and liquid, we can easily integrate them with the current infrastructure for storage and for transportation. So basically, you store the renewable energy in the form of chemicals. And if we make like precursor for polymer, for example, so we can store the CO2 in type of those materials. So with the low carbon footprint electricity, you can even make a carbon negative process. So how does this technology work? Just to make sure we are on the same page, introduce a little bit about the fundamental of this process here. So electrochemical CO2 conversion is a electrochemical process. So basically you have a cathode and anode. They are usually separated by a membrane. And during the reaction, like you oxidize normally the water on the surface of the anode to generate oxygen and electron and proton. And these go through the cathode side where the CO2 is converted to your desired product. Now, it depends on the type of the catalyst that you use. You can make different type of products. In the gas phase, you can make carbon monoxide, methane, and ethylene. In the liquid phase, you can make alcohols and acids, for example. So this is very exciting thing that you can make different type of products, especially on copper catalyst. But it's also challenging because now you need to find a way to control the reaction so that you can make a single product so that you can avoid the separation in the downstream processes. So in terms of the system, so basically, if you want to perform the reaction at high reaction rate so that you can decrease the capital cost of the system, one of the systems you need to work on is the gas phase CO2 system, where the CO2 is fed into the system from the gas phase, go through a porous layer, which is the gas diffusion layer, to the surface of the catalyst. So here on the left-hand side, I show just a schematic of a electrochemical cell that you have the cathode, you have the membrane, and anode here. So the electrolyte here can be either liquid phase, which is the flow cell that I'm going to present in a minute, or you can use the electrolyte in the solid phase, the polymer phase, or this is the membrane electrode assembly system. So if we zoom in here, the gas diffusion layer, there are two main components. That's the gas diffusion layer here, the hydrophobic and porous one, and the catalyst layer where the reaction occur on the surface of the catalyst. So our one of the main tasks for us is now how we design that gas diffusion layer so that we can bring CO2, we can bring the water, and we can bring electron to the surface of the catalyst at the same time. And that is one of the, it sounds simple, but it's not kind of straightforward because like water is liquid phase and then CO2 is gas phase, and electron normally you go through the solid conductive substrate. So somehow we need to bring them together. So that is like one of the main focus that I have been working on in the last few years. So when we start working on electrochemical CO2 conversion in the gas phase, we use commercial carbon gas diffusion layer So basically, for the commercial one, you have like 2 layers of like the carbon fiber and microporous layer on top with a different hydrophobicity, so that you can it allows the gas diffuse through that, and it blocks the water penetrate through the pore of the gas diffusion layer. So we use this gas diffusion layer, and then we deposit the copper catalyst on that to make different products. So we use physical method. So this is the variable deposition, and we control the thickness of the sample. For example, we change the thickness from 10 nanometer to 1000 nanometer. So this is the nominal thickness, and when you change the nominal thickness, you change both the particle size and also like the thickness of the sample, as you can see here. Now, using this catalyst, we perform it in a flow system where we use very high alkaline electrolyte. And so we change the concentration of the electrolyte, and then we found that higher electrolyte is more helpful. It's increase the selectivity of the system. So we use the 10 molar KOH here, potassium hydroxide. So on the left-hand side, I show here the dependence of ethylene Faraday efficiency versus the current density. So what we observed was the thinner catalyst normally exhibit higher Faraday efficiency with the maximum selectivity we achieve at around 65% at a current density of 250 to 2070. And interestingly, like we observe this high performance at pretty low overpotential. So it's confirmed that like the hydroxide help to increase the selectivity for C2 products. Okay, so it worked like pretty well in terms of selectivity, current density, and low overpotential. But one of the problems we observe is the stability of the system, where when we perform the stability test, the selectivity dropped like pretty quickly, like within an hour or so. So ethylene, the residual here. And at the same time, we observe the hydrogen increase. So there's a few things can happen, either the gas diffusion layer or the catalyst layer change with time. We found out later on that the gas diffusion layer, the carbon layer, is the main reason for that quick degradation of the electrode, because it changed from hydrophobic before the reaction to like a little bit more hydrophilic after the reaction here. And when it becomes hydrophilic, the whole gas diffusion electrode will be filled with the water, and it's blocked the diffusion of CO2. So there's few reasons for the changing on the surface of the gas diffusion layer. So by that time, we did some quick characterization showing that we have like some increase of the oxygen contents within like that. The hydrophobic surface of the carbon has been changed during the reaction. And there's other reason, could be the formation of the zone in the pore of the gas diffusion layer. And just recently, the group from Dr. Berdini showing that like is the potential dependent. When you apply a very negative potential, it causes the degradation of the surface of the carbon layer. So one of the ways that you can think of to overcome this problem is trying to make the more active catalyst to reduce the applied potential units. By that time, we did not know that, so we choose the other way of like, instead of using the carbon-based gas diffusion layer, we turn our attention to the PTFE, which is just purely PTFE hydrophobic layer. So it's a filter made of PTFE fiber, and then we deposit our catalyst on that using the sputtering method. And because at that time we thought, okay, because of the thickness of the catalyst is very thin and the electrical conductivity maybe is not high enough. So the idea is we need to add a little bit of conductive material on top to increase the conductivity. So we add a layer of the carbon nanoparticle and graphite on top so that we can improve the conductivity. But later on, I think that you may be aware of the last talk from Dr. Garcia last time that the role of the carbon and graphite layer is not just the conductivity. And one of the reasons is we add some naphthalene on the carbon and then it's helped the diffusion increase the diffusion of CO2. And that is another side effect that we did not expect. So to develop those electrodes, we start with the PTFE membrane here. At the SCM, you will see that the pore is around 300 to 300 nanometer to about 1 micron or so. And then we spat the copper on top of it. We use a spray coating to coat the carbon nanoparticle and then the graphite on top. So it's multiple steps. So what we found is this it worked pretty well in terms of the maintaining the selectivity. So as you can see here, we run the reaction for about 150 hours. We can maintain the selectivity for ethylene of more than 60%, 65%. And at the same time, when we compare the catalyst with the carbon-based get diffusion layer, it lasts for about an hour, as we mentioned previously. We also are trying to play with the different composition where we add either with and without the carbon layer in there. So that would be the blue data here. And without the carbon layers, it's less stable and it's also less selective. So meaning that like the carbon layer is not just improve the stability, but also like play a role for the selectivity also. So that's what we observed, and we did characterize the electrode after the reaction and still observing the multiple layer when we design the catalyst from PTFE and then copper and then carbon layer there. Okay, so far we work on the CO2 conversion using the very high alkaline electrolyte in the flow cell system. And one of the problems that we observe is that when we try to calculate how much CO2 go to the product, how much CO2 go to the carbonate, and it turns out that a lot of CO2 go to the carbonate. So if we use those systems, there would be a lot of energy needed to regenerate the electrolyte. So you can think of the different way of overcome that problem using neutral electrolyte, for example. But in the neutral electrolyte and in the flow cell configuration, so on the left-hand side, you can see here we have an electrolyte going through between the cathode and the membrane. So the conductivity, the ionic conductivity of this layer is very important. And normally the neutral electrolyte is, the ion conductivity is not so high compared to the alkaline electrolyte. So instead of using the neutral electrolyte for this system, we turn ourselves into the new platform for neutral CO2 reduction, and that's the membrane electrode assembly system. So in the membrane electrode assembly, we do not have any liquid electrolyte between the cathode and the membrane, and the cathode membrane and anode now press against each other and then forming a zero gap between them. So the good thing about that is that you can avoid the effect of the electrolyte, especially if you use a high concentration, the zone formation in your catalyst layer and the gas diffusion layer would be a problem. And then this configuration is similar to the PEM system, the water electrolyzer. So if you know how to make it effectively, you can kind of quickly integrate them into the large system with the commercially available electrolyzer. So that is another good thing. And removing that liquid layer, you can also reduce the ohmic loss. And so there's another good thing about this one, but there's also a challenge. So when we move from flow cell to the MEA system, so we use the same catalyst, so the same PTFE, copper, and carbon here, and then we want to see how it's performed in the MEA system. So we found that in the MEA configuration with the same catalyst, we can still run a pretty high current density, up to 200 milliamp. The problem here is the selectivity for ethylene is decreased a little bit. So the maximum we have is around 50% or so at a current density of around 200 milliamp. Even though we have the pretty good liquid product, ethanol also, but over it seems like ethylene reduced. Nevertheless, we can perform the reaction at pretty stable state, maintaining the selectivity for ethylene of around 40%. It's about 100 hours. So during the reaction, we can maintain the good selectivity, even though the current density is pretty low in the range of 100 to 125 milliamp per square centimeter. So, so that is like, so that's what we learn, like when we move from flow cell, where we can control the electrolyzer, we can optimize the selectivity. But when you move to the MEA where you do not have that advantage, so we need to turn ourselves kind of like think about how can we improve the performance from the catalyst point of view. Now we need to design the catalyst for this process. So there's a few different ways we can improve the performance of the copper on PTFE. So starting with the pure copper on PTFE, you can either make a hybrid system, like combining copper with other elements or other oxide hydroxide, making a hybrid system to change its selectivity and performance. The other approach is that, like, so far we just spot the copper on the surface of the PTFE. Can we change the surface property of the copper using whatever methods that make that copper more selective? So that is another strategy. Another one would be now trying to play with the reaction environment on the surface of the copper by coating the copper with the other component, like the polymer, for example, so that we can have the confined reaction space, we can change the reaction pathway. So there are like quite a general strategy. So over the past few years, we did a lot of work on those strategies to improve the performance of the copper on PTFE in general, and also for the MEA application. So I just want to show a few examples here. So one of the work that we try to improve the performance of the copper on PTFE is like trying to change the surface of the copper. So what we found is that when we make the catalyst under the CO2 reduction conditions, meaning that you grow the copper while you are performing CO2 reduction condition, in that condition, we produce copper with more copper 100 phases exposed. And from many previous work has shown that when you have the copper 100 phases, it's more selective for CO2 for C2 products. So so that's where we try to implement this idea on the copper on PTFE to see if we can improve the performance in the MEA system. So now, because we need to grow more copper on PTFE, so we start with a very thin layer of copper on PTFE. So usually we grow about like 200 to 300 nanometer of copper on PTFE. Now we reduce it to 50 nanometer. It's just a seeding copper. And then we grow the copper nanoparticle on top of that copper on PTFE. So this one is we grow the copper for at 400 milliamp for about 60 seconds. So as you can see here, we observe the growth of the copper nanoparticle on that PTFE. And we characterize the samples, and we found that it's a bit more like copper 100 phases. So when we implement this catalyst on the MEA system, as you can see here, we perform on the full cell voltage of 3.7 volt and a MEA with a surface area of 5 square centimeter. So we can maintain the ethylene selectivity at around 55 to 60% for about 60 hours. And impressively, like we achieve at a current density of around 300 milliamp, which is quite impressive for the MEA system. So far, yeah. So in one way that if we make a better copper, we can improve the performance of the system. So that's the conclusion from this work. The second example I want to show you is using the core cell structure. So this work was performed by Dr. Lee in collaboration with other group at Caltech. So instead of using bare copper, we deposit a layer of the pyridinium polymer on the surface of the copper. And what we found is that that polymer layer, it lowered the activation barrier for CO coupling on the surface of the copper. So in principle, you have two types of CO adsorption on the copper surface, which is a CO bridge or a CO atop. So CO bridge is attached to the copper is much stronger compared to the CO atop. So when we have the polymer layer, it stabilizes the CO atop adsorption. And from the DFT calculation, we found that the coupling between the C atop and CO bridge is much more efficient compared to coupling of the two CO bridge. So that is from the theory point of view. Experimentally, when we perform the reaction in, so this one is in the flow cell first, and we use the neutral electrolyte, 1 mole bicarbonate electrolyte. As you can see here, with the polymer coating on the surface, we can improve the selectivity for the ethylene, increasing from 40 to 50 to around 60 to 70%. So about 20% increase in ethylene selectivity. And if we look into what is the product distribution in these two systems, and it turns out that the total selectivity for ethylene and carbon monoxide of the two samples are pretty much the same. But what the polymer layer help is it shift the CO into the ethylene in that condition, so that it improves the selectivity for ethylene while decrease significantly the selectivity for carbon monoxide. As you can see here, the ethylene go up and the carbon monoxides go down for the polymer coated sample. So that's further confirmed that the role of the polymer, how is help to improve the catalyst. And because now your catalyst work well in the neutral system, we want to implement in the MEA system. So in the first upper panel here is the product distribution, and the similar product distribution trend we observe for pure copper and polymer on the copper, with the ethylene in the range of around 40–45% for pure copper, and the ethylene for polymer coated sample is around 60% here. And when we perform the stability test, we can maintain the reaction for about 180, 590 hours with the ethylene selectivity of around 65% here. So it showed that with the same copper, if we modify the surface to improve the selectivity in the neutral condition, we can improve the performance for the CO2 in the MEA system to multiple carbon product. So just to make sure here, the total current density is the 600 milliamp for 5 square centimeter electrode. Okay, so far we have discussed the polymer-based electrode. I will show you that using that PTFE electrode, we achieve good selectivity, we achieve good stability for CO2 conversion to ethylene. One of the problems with this structure is the scaling up ability. Because imagine when you have the small cell, 1 square centimeter or 5 square centimeter, you can easily distribute the current from the outer of the electrode. Now, if you go the larger area, you need to find a way to design the current distributor so that electron can go from anode to the cathode there and go to the catalyst. And that is very challenging in terms of CO2 reduction, either for flow cell or for MEA system, because whatever conductive substrate you use for the current collector, and that substrate is going to be in contact with the electrolyte, and then it's going to generate the hydrogen. So that is the very challenging problem for PTFE base. So we continue to work on that, trying to come up with the modified PTFE design. Hopefully that we can overcome that problem. But in the short term, we want to overcome this problem by revisiting the carbon-based gas diffusion electrode. So I mentioned to you that the carbon-based, it did not work when we work on flow cell, when we try to do the CO2 reduction for both CO2 to carbon monoxide and for ethylene. But now we know that if we operate in the MEA system, we have a better chance to improve the stability. So we thought maybe we have a chance to work with the carbon-based gas diffusion electrode. And of course, now if we use directly commercial carbon-based gas diffusion layer, it did not work. It still degrade pretty quickly. So we modify the gas diffusion layer by using the metal substrate, and then we improve the hydrophobicity by making our own microporous layer. So our goal for this one is trying to see if we can perform the reaction stably. So the first one, we perform the reaction in the small cell, 5 square centimeter, similar to the one that I presented previously. And the selectivity is nowhere near what we observe for the PTFE base. But the good thing is that we can maintain the selectivity for ethylene around 30%. For a period of around 400 hours or so, and then we stop. It's constant, it's quite constant. So we did not observe the degradation of the ethylene selectivity, which is a good thing. Hydrogen keeps at around 30%, and carbon monoxide is 10 to 20%. And as you can see here, so we can run the reaction at 200 milliamp for about 400 hours. So the cell voltage is pretty large, 4.2 volt. So there's a few different things in here to maintain, especially when you work on the MEA, you will see that the problem is not just the cathode, so we need to modify the membrane, we need to modify the anode, so it ends up increase the total cell voltage a little bit because we want to operate for a long time and at large scale. Even though the selectivity is not what we expect, but we are happy that it worked for the stability. Later on, when we optimize the catalyst a little bit, we can improve it to the about like 40 to 50% selectivity. But we continue working on that to see if we can maintain that selectivity at for a long time. So we also use the same electrode, and then we try with a larger scale, like going up 10 times in surface area. So we test the catalyst in the MEA system with the 50 square centimeter cell, and we observe a similar trend, and maintaining the ethylene of around 30%, and with a similar trend on hydrogen and carbon monoxide also. Even though a little bit different here is that we increase the cell voltage a little bit with the larger cell, and we can maintain the system for about 150 hours on that large scale. So over, like, what we observe is if we modify the carbon electrode, we have a chance of perform the reaction for a long time, but still a lot of work to do in terms of improving the selectivity. And maybe one point I want to point it out before I conclude my talk is you will see like the selectivity go up and down, and when you did when you do the experiment yourself, you will see that that is a tricky thing of like the electrode like constantly changing with time, and then and one of the reasons is the zone formation in the pore of the gas diffusion layer that we need to wash out the zone so that we can recover the selectivity. So that is another challenge that I want to point it out here. Okay, so like CO2 conversion, there's a lot of challenging, well, there's a lot of opportunity first, but a lot of challenge facing this technology. So overall, you have the problem from all over the place, like from the cathode, from the membrane, from the anode, and also the problem with the scaling up. So there's a lot of challenge in there. I cannot comment on the other sides, but from the cathode side, in terms of designing the gas diffusion electrode, so what we can conclude is that like the modified the PTFE-based GDL is stable. So if you can find a way to design the current distributor for that, so that should be a good start for the stability system. You can also think about the modified carbon GDL, and what we observed so far is we believe that if we do the right thing, we would be able to overcome the stability problem with the carbon base. Now, the second thing is, so far we try to bring all of the reactant to the surface of the catalyst, the carbon dioxide, water, and electrons. We try to bring them to the one location on the surface of the catalyst. It worked for us to start the reaction. But once you start the reaction, there's other thing to consider. Now, one of the problems is the zone I mentioned, that when you use in the anode side with the MEA system, so it can diffuse through the membrane, and then it's accumulate into inside the pore of the GDL and blocking the diffusion of the CO2. So the zone is problem. Now, the other problem is the product itself. Now, imagine if you make the gas product like carbon monoxide, ethylene is work great. And if you make the liquid product like formic acetic acid, like ethanol, for example. So the ethanol is hydrophobic, and then it can penetrate into the pore, the hydrophobic pore. And so, and finding the way to constantly remove that liquid product is also you need to overcome if your target product is the ethanol instead of the gas product. The third point is about the catalyst itself. And so far, we observed the catalyst. The stability of the catalyst is in the range of few hundred hours, but at a pretty low current density. So that's the last point. Nice. One of the questions would be, what would happen if we increase the current density to 500 milliamp or higher, what would happen? I mean, in terms of the gas diffusion layer, does it change? Like, because the higher current, meaning that more negative potential, so the carbon base tend to degrade faster. Also, like the surface of the catalyst may reconstruct, that has not been explored well in the flow cell system and MEA system. And now, if you want to improve the catalyst, the selectivity, one of the key things is to control the catalyst. Now, you do not have a chance of turning the narco environment with your electrolyte, liquid electrolyte. So think about like kind of adding or like modify the surface of the catalyst so that you can mimic that environment, try to create the environment by controlling the diffusion of the ion or a cation or an ion to the surface of the catalyst to make it work for the MEA system. So those are like few different things that I can think of in the near future if you want to make a stable gas diffusion electrode. And with that, I would like to thank, so most of the work I presented here is, that's what I did as a postdoc. So I would like to thank my previous group here. It's a huge group and a lot of company and funding agency to support our work on CO2 to ethylene and also the carbon spray. And with that, I would like to finish my talk, and I'm happy to answer your question.